So, as we discussed in the last class, this from this week onwards, we will be having a review of fourth and fifth module. Okay, so all of you have already gone through those modules, so we will be having a quick review. Okay, so that you can have a refresh of the things you have already studied. So, we will start with the fourth module first. So, here the first thing we have to study in the fourth module is the basic principle of beam steering. Okay. So, what is mean by beam steering? Beam steering. The name itself will give you an idea. Okay. You all will be familiar with the steerings of our motor vehicles. Motor vehicles are having steerings. Okay. So, for what purpose they are using the steering? Or for what purpose the steerings are provided with the motorcycle or with the motor vehicles? For what purpose the steerings are provided with the motor vehicles? It is for changing the direction of the vehicle. Okay. So, beam steering means it is the process of changing the direction of beam. That's it. And how it can be achieved, that only we are going to see. Okay. So, we will see how beam steering or changing the direction of beam can be achieved. So first sentence says the basic definition is the process of changing the direction of the main lobe of a radiation pattern. Okay. The direction of beam means it is the direction of main lobe. Okay. Always beam implies main lobe. Right? Because the main lobe is supposed to be in the direction of desired communication. Okay. Main lobe is supposed to be in the direction of desired communication. So that will be the direction of beam, or we want to send beam in that particular direction where the main lobe points. Okay, so it's the process of changing direction of main lobe of a radiation pattern. And how it can be accomplished? That is the next question. Okay, we know what is the definition of beam steering, that we know. Then how it can be achieved? That's the next question that we are going to address. Beam steering may be accomplished by switching the antenna elements or by changing the relative phases of the RF signals driving the elements. Okay. So, anyway, the frequency we are going to use for a particular set of antennas are same. Okay, whether it is a broadside case or an end-fire case, the frequency that we are using will be same. Same frequency signal only we will be feeding all the elements. Okay. So it can be achieved by switching the antenna elements or by changing the relative phases of the RF signals. That only the second thing only we are going to address. Switching the antenna elements means what? We can switch in between the antenna elements so that the direction of radiation or direction of main lobe maxima will be changed. That is basically just rearranging the antenna elements in the array. Okay. So that is quite understandable. If you are rearranging the antenna elements in the array, of course, the direction will change. Okay, the next, by changing the relative phases of the RF signal driving the elements. That is the thing we have to see. How to change the relative phases, or on all antenna elements, we are using the same frequency signals. Okay. And what we are going to change? We are going to change the phases. Okay. So phases of the signals driving the elements we are going to change. In antenna arrays, the main lobe is steered via phase shifters to the direction of interest. And how the phase we are going to change? The main beam is steered by phase shifters. Okay. We are using phase shifters. Okay. What is a phase shifter? Basically, what is a phase shifter? It is nothing but an arrangement to shift the phase. What can be it? Any suggestion, or have you ever heard of a phase shifter? Any circuitry which can be used to change the phase? Any answer? Any circuit, have you ever come across any circuit which can change the phase of a signal? At least EC one student should answer, I think. I only conducted lab for that. Maybe you are in sixth semester, none of you have come across a circuit, a basic circuit which is capable of changing the phase of a signal. Amplifier. Hey, amplifier 180 degree phase shift will be there. But that is for amplification basically. Okay, that is a phase shift is there, that is a byproduct of amplification. Basically, we are using that for amplification. Or simple. Don't go for that much complicated things. Amplifier is meant for amplification. Just for phase shift. Just for phase shift, what we can use. RC phase shift oscillator that are just a phase shift is there, but that is an oscillator. Basically, we are using RC phase shift oscillator. That RC network is to provide phase difference. 3 RC networks we are using. RC phase shift oscillator. What's the basic principle of RC phase shift oscillator? 180 degree phase shift will be provided by the transistor. Then remaining 180 degree phase shift should be provided in order to meet the Barkhausen criteria. Okay, A beta equal to 1 or total phase shift will be equal to 360 degree. For that, 180 degree phase shift is already provided by the transistor. Then rest 180 degree phase shift we have to introduce. For that, what we are doing? We will use RC. 3 RC networks we are using. Okay, each will be giving a phase shift of 60 degree. I think you might have studied, not you might have, you have studied this in your 3rd and 4th semesters. Okay. So in that, just use an RC network. One resistor and capacitor is enough. Okay, one resistor and capacitor is enough to impart phase difference. RC phase shift oscillator, that phase shift part we are doing like this only. Okay, just by introducing a network of capacitors and resistors, we can achieve the phase shift. Okay, so a phase shifter basically we can achieve just by using the resistor and capacitor. Okay, a transistor will be having a 180 degree phase shift. So we can just use a transistor to have 180 degree phase shift. Okay. But the very basic thing is we can use what? An RC network to impart phase shift. There is nothing complicated. One resistor and capacitor, 2 basic elements of our electronics are required to impart phase shift. Okay. The main beam is steered by phase shifters to the direction of interest. So the main beam we can steer or we can change the direction of the main beam by using phase shifters. That means we are supplying currents or driving currents of different phases to each element. Okay. So we will see how that is happening. These arrays are called phased arrays or scanning arrays, since each and every arrays are fed with an RF signal which is having phase shift. Okay. The process is referred to as electronic beam steering, and in this process, the phase of the current at each antenna element is changed directly. That we already discussed. Same thing only. The current we are supplying to each of the antenna elements, they are changing directly. Then, by using that, how this change in directivity or change in main beam occurs, that is, we are going to see next. The phase of the elements are shifted in such a way that they produce constructive or destructive interference so as to steer the beam in the desired direction. That's it. It is as simple as that. Okay. That means we are giving a current which is having different phase shift or which is having different phases to each and every element. Okay. RF current we are basically giving, or RF signal we are basically giving to each and every antenna elements in an array. Okay. So while giving that itself, we will change the phases by using phase shifters. Okay. So by doing that, what is basically going to happen? The same signal with different phases are going to be radiated from each and every element. Okay, the same signal, which is having different phases, are going to be transmitted from the antenna elements. So if we are having such a system of signals with same frequency and different phases, what is going to happen basically? And they are located closely also. If they are located in an array, so they are located very closely. So in such a case, suppose some 10, 15 elements, antenna elements in an array, they are located, and each and every element is driven with the same frequency, but different phases. Okay, same frequency, but different phases, and all are started to radiate the same signal, but with some phase difference. What is going to happen basically then? Under this condition, what is going to happen? Yes, interference. Correct. They will interfere each other. Okay. Same frequency signals with different phases, they will interfere each other. So you might have studied constructive and destructive interference. Okay. There is constructive interference and destructive interference. If the phase difference between the signals are in such a way that their maximas are coincides. Okay, their maximas are coinciding. What will happen? Basically, those maximas will add up. Okay, a signal means a sine wave. Okay, signal means a sine wave only. Sine wave is having a maxima and a minima. The next sine wave, suppose some 10 elements are there. The first element is radiating a sine wave. The second element is radiating a sine wave, but it will be just shifted, or a phase will be shifted. Okay. Suppose first element is radiating a sine wave, and second element is radiating a sine wave shifted by 90 degree, or sine wave having phase shift 90 degree. What you will call a sine wave with phase shift 90 degree? A sine wave with a 90 degree phase shift. What you will call it generally? A sine wave with a 90 degree phase shift, or sine 90 plus theta. Yes, cosine. Okay. So a sine wave with 90 degree phase shift is a cosine wave. Okay. So if they are interfering each other, what will happen? Whenever whenever the sine wave is going to maximum, cos wave is going to minimum. Okay. So if a sine wave and cosine wave, or if both waves with 90 degree phase shift, they are interfering each other, whenever the sine wave is maximum, at that time cos wave is minimum, and whenever the cos wave is maximum, at that time sine wave is minimum. So what will be the effect? What will be the result? These two are interfering. What will be the result? 0. Yes. They will cancel each other. It will be 0. Okay. The sine wave and cosine wave, both are complementary. Whenever the sine wave is maximum, the cosine will be minimum. Whenever the cosine is maximum, sine will be minimum. So that will, what will happen? That will destructively interfere, we can say, because the net result is 0, or both are destroyed. That is called destructive interference. Okay. And next case, we will take waves with same phase difference. Suppose they are interfering. Two sine waves. Suppose two sine waves are interfering. So whenever the first sine wave is maximum, the second sine wave is also maximum. Okay. Whenever the first sine wave is minimum, the second sine wave is also minimum. So what will be the result? The result will be the addition of both. Or we can say that they are interfering constructively. Okay. They are interfering constructively. This is the basic difference between destructive interference and constructive interference. And here in an antenna array, we are supplying the all elements with some phase difference. Okay, some relative phase difference. We are supplying all elements. Okay. So what we can expect? We can expect some constructive interference and some destructive interference. Okay. So we will see in whatever direction the constructive interference takes place and whatever directions the destructive interference takes place. So basically, in the directions in those which constructively these waves are interfering, that will be having the maximum directivity, or the major lobe will be directed in that particular direction where the waves are constructively interfere, and all other parts where the waves are destructively interfering, that will be having minor lobes. Okay, so only in one particular direction only the maximum constructive interference takes place. So by using this property, we can steer the beam by just supplying each and every element with a different phase. Okay, the same signal only. Anyway, same signal only we are sending. Same signal means same frequency. Okay, same frequency only we are using, but we are just changing phases of each and every element while supplying itself by using simple phase shifters. So what will be happening? Constructive interference and destructive interference will take place, and in that particular direction where the interference is constructive, there the beam width will be maximum, or the directivity will be maximum in that particular direction. So this is as simple as that. Okay. So the properties of these arrays remain static with time. Remain static with time means what? It is not going to change with respect to time, since we are not going to change the phases with respect to time. Okay. Then advantages: high gain and low side lobes. Okay, high gain means you can say that lot of elements are there and they are constructively interfering, means that is high gain, and side lobes will be low, because the constructive interference will take place only in one direction, and in all other direction the interference will be destructive. Okay, so side lobes will be low. Ability to permit the beam to jump from one target to another in few seconds. Okay, this is due to the change. If we are just changing the phases in a different pattern, this constructive interference will jump directly from one direction to another direction. So the beam also will jump accordingly. Okay. Free eligible dwell time. Okay. That means we can have this beam at for how long we want to have that particular one. Suppose if you want to steer the beam for for 10 hours or for 10 seconds, that is also possible. The dwelling time of the beam is free. That there is no restrictions for that. Okay, because we are just what we want to do basically for that particular duration. We want to feed the elements with a particular phase shift. That is possible with by the use of phase shifters. So there is no other quantity which is defining this particular beam steering. So the free eligible dwell time is possible. Okay. Even if one element fails, system remains operational. Okay, anyone can justify that. Can anyone justify that? Even if one element fails, system remains operational. How that's possible? How that is possible? I'm having 10 elements, and I've fed all the 10 elements with different phases. So in that one antenna is not working. Still, I can achieve beam steering in a particular direction. How that can be possible? How that can be possible? Nobody is answering. Okay, that is possible because here we are using interference. Okay, if 10 waves are interfering and 9 waves are interfering, means there is no difference in the direction. The constructive interference will be in the same direction only. The only difference is one source is not working. That may reduce the directivity a little, but still the particular direction, the main beam, the major lobe will be in that particular direction only. It won't affect the direction of the major lobe. Okay, it may affect a little of the directivity, or what we can say, the extent to up to which the major lobe lies. That can reduce a little because now earlier 10 waves were constructively interfering. Now only 9 waves are constructively interfering if one element fails. That is only the difference. Okay, but it won't affect the direction of major lobe. The direction of major lobe will be the same since it is not at all going to affect the interference. If the interference is to be affected, means all the relative phase differences of the elements has to be changed. Okay, that we are only doing by the use of phase shifters. Okay, so I will take your attendance. Today attendance is very less, only 88 people are there. ഓക്കെ, നിങ്ങളോട് ഞാനൊരു കാര്യം പറയാനുണ്ട്. നിങ്ങളുടെ സീരീസ് എക്സാംസ് ഏകദേശം എല്ലാവരുടെ ആൻസറൊക്കെ സെയിം ആയിട്ടാണ് എഴുതിയിരിക്കുന്നത്. ഓക്കെ, എനിവേ ഞാൻ അങ്ങനത്തെ കാര്യങ്ങളൊന്നും മൈൻഡ് ചെയ്യുന്നില്ല. ആൻഡ് അതിൻ്റെ അകത്തൊരു കാര്യം പറയാനുണ്ട്. നിങ്ങൾ ഫസ്റ്റ് ആൻഡ് സെക്കൻഡ് സീരീസ് സ്കിപ്പ് ചെയ്ത ആൾക്കാരുണ്ട്. ഫസ്റ്റ് ആൻഡ് സെക്കൻഡ് സീരീസ് സ്കിപ്പ് ചെയ്ത കുറച്ച് ആൾക്കാരുണ്ട്. ഫസ്റ്റ് സീരീസിൻ്റെ ഞാൻ പറഞ്ഞിട്ടുണ്ടായിരുന്നു പർട്ടിക്കുലറായിട്ട്. സെക്കൻഡ് സീരീസ് ഞാൻ നോക്കിയപ്പോൾ 3-4 പേര് കണ്ടു. അപ്പോൾ അതവരെ ആരും ഞാൻ പേഴ്സണലി കോൺടാക്ട് ചെയ്യാനൊന്നും ഉദ്ദേശിക്കുന്നില്ല, അതിൻ്റെ ആവശ്യമൊന്നുമില്ല. അപ്പൊ അങ്ങനെയുള്ള ആളുകൾക്ക് ഇന്റേണൽ മാർക്ക് വേണം എന്നുണ്ടെങ്കിൽ, അതായത് ഫസ്റ്റ് ആൻഡ് സെക്കൻഡ് സീരീസ് 2 സ്കിപ്പ് ചെയ്തിട്ടല്ല, 2 സ്കിപ്പ് ചെയ്ത ആൾക്കാർക്ക് എന്തെങ്കിലും ചെയ്യാൻ പറ്റുമെന്ന് എനിക്ക് തോന്നുന്നില്ല. ഇപ്പൊ ഫസ്റ്റ് ആൻഡ് സെക്കൻഡ് സീരീസ് സ്കിപ്പ് ചെയ്തവര് ആരെങ്കിലും ഉണ്ട് എന്നുണ്ടെങ്കിൽ അവര് ഞാൻ ഈ ഫ്രൈഡേ അല്ലെങ്കിൽ സാറ്റർഡേക്കുള്ളിൽ വിത്തിൻ ദിസ് വീക്ക് ഞാൻ നിങ്ങളെ ഇന്റേണൽസ് പബ്ലിഷ് ചെയ്യും. ഓക്കെ, അപ്പോൾ ഫസ്റ്റ് ആൻഡ് സെക്കൻഡ് സീരീസ് സ്കിപ്പ് ചെയ്ത ആരെങ്കിലും ഉണ്ടെങ്കിൽ അതിന് മുന്നേ എന്നെ കോൺടാക്ട് ചെയ്യുക. വേറെ ഏതെങ്കിലും ഒരു എക്സാമോ എന്തെങ്കിലും കഴിഞ്ഞോ നടത്തിയിട്ട് അവർക്ക് ഇന്റേണൽസ് അഡ്ജസ്റ്റ് ചെയ്യാം എന്ന് ഞാൻ വിചാരിക്കുന്നു. ഓക്കെ, അപ്പോൾ അതിൽ കൂടുതലായിട്ട് എന്തെങ്കിലും ചെയ്യാൻ പറ്റുമെന്ന് എനിക്ക് തോന്നുന്നില്ല. അപ്പോൾ അങ്ങനെയുള്ള ആരെങ്കിലും ഉണ്ടെന്നുണ്ടെങ്കിൽ അവർ തന്നെ എന്നെ കോൺടാക്ട് ചെയ്യുക. അവർ ഇതിൻ്റെ അകത്ത് ക്ലാസ്സിൽ അറ്റൻഡ് ചെയ്യുന്നുണ്ടോ എന്ന് എനിക്കറിയില്ല. അവരെന്നെ കോൺടാക്ട് ചെയ്യുക. അപ്പോൾ കോൺടാക്ട് ചെയ്യുമ്പോൾ നമുക്ക് മാക്സിമം വേറെ എന്തെങ്കിലും അതിനൊരു സൊല്യൂഷൻ കണ്ടുപിടിക്കാൻ നോക്കാം. അല്ലാന്നുണ്ടെങ്കിൽ ഞാൻ അസച്ച് ഇന്റേണൽ ഇടും. അത് കഴിഞ്ഞതിന് ശേഷം പിന്നെ എൻ്റെ അടുത്തോട്ട് ഇന്റേണൽ പറഞ്ഞു അങ്ങനെയുള്ള കാര്യങ്ങൾ പറഞ്ഞുകൊണ്ട് വന്നു കഴിഞ്ഞാൽ ഞാനിത് ചെയ്യും. ഓക്കെ, അതുപോലെ തന്നെ ഞങ്ങളുടെ അസൈൻമെന്റ്സ് ഒക്കെ എല്ലാവരുടെയും ഇ ടി ലാബിൽ ഞാൻ കഴിഞ്ഞ ആഴ്ച അവർ പറഞ്ഞായിരുന്നു, ഇ ടി ലാബിൽ അസൈൻമെന്റ് അപ്ലോഡ് ആയത് നിങ്ങൾ നോക്കണം എന്ന് പറഞ്ഞിട്ടുണ്ടായിരുന്നു. അപ്പോൾ ആ കാര്യങ്ങളൊക്കെ നോക്കുക. ഓക്കെ, ഇന്റേണൽസ് എന്തായാലും ഞാൻ ഈ ആഴ്ച വിത്തിൻ മാക്സിമം സാറ്റർഡേയോട് കൂടി പബ്ലിഷ് ചെയ്യണമെന്നാണ് ഞാൻ വിചാരിക്കുന്നത്. അതിനു മുമ്പേ ഞാൻ ഈ പറഞ്ഞ കാര്യങ്ങളൊക്കെ നിങ്ങൾ ശ്രദ്ധിക്കുക. പിന്നെ നിങ്ങൾക്ക് ഞാനൊരു 4th and 5th മൊഡ്യൂള് ഒരു എക്സാം ഇട്ടിട്ടുണ്ടായിരുന്നു. സോ ഐ വിൽ ബി ടേക്കിംഗ് മാർക്സ് ഫ്രം ദാറ്റ് ആൻഡ് ഐ വിൽ ബി ടേക്കിംഗ് ദ ആവറേജ് ആൻഡ് ഐ വിൽ ബി കമ്പയറിംഗ് വിത്ത് ദ 2 സീരീസസ്. ഓക്കെ, അതായത് നിങ്ങളുടെ 2 സീരീസ് ഉണ്ട്, പ്ലസ് 4th and 5th മൊഡ്യൂൾസിന്റെ എക്സാം സെപ്പറേറ്റ് ഇട്ടിട്ടുണ്ടായിരുന്നു. അപ്പൊ അതിന്റെ മാർക്കും കൂടെ ചേർത്തിട്ട് ഈ 3ൽ ബെസ്റ്റ് ഓഫ് 2 ആയിട്ട് എടുക്കുക. എനിക്ക് തോന്നുന്നത് മോസ്റ്റ് ഓഫ് ദ ആൾക്കാർക്ക് അത് സീരീസ് തന്നെ ആയിരിക്കും. ബിക്കോസ് 5th മൊഡ്യൂളിന്റെ ഒക്കെ എക്സാമിന് മാർക്ക് വളരെ കുറവാണ്. മിക്ക ആൾക്കാർക്ക് പ്രോബ്ലംസ് ഒക്കെ എല്ലാവർക്കും തന്നെ തെറ്റിട്ടുണ്ട്. ഓക്കെ, അപ്പം ഈ മൂന്ന് ഇതിൻ്റെ അകത്ത് ബെസ്റ്റ് ഓഫ് 2 ആയിരിക്കും ഞാൻ ഇന്റേണൽസിന് വേണ്ടിയിട്ട് എടുക്കുക, അതായത് ഫസ്റ്റ് സീരീസ് ആൻഡ് സെക്കൻഡ് സീരീസിന് മാർക്കായിട്ട് എടുക്കുക. ഓക്കെ, എല്ലാവർക്കും തന്നെ അത് ബൈ ഡിഫോൾട്ട് ഫസ്റ്റ് ആൻഡ് സെക്കൻഡ് സീരീസ് മാർക്കാണ് വരിക എന്ന് തന്നെയാണ് എനിക്ക് തോന്നുന്നത്. 1-2 പേർക്ക് വലിയ മാർക്ക് വന്നാലും വലിയ മാറ്റം ഉണ്ടാകും തോന്നുന്നില്ല. Okay, anyway, effectively that will be first and second series only. But if somebody has performed well in that fourth or fifth module tests, that will be counted. Okay. Yes, I will come back to our topic. Then the disadvantages: only 120-degree coverage in azimuth and elevation is the 120-degree coverage is only it is applicable. And it is a very complex structure because we have to make use of the phase shifters and all, and we have to be very accurate in the phase shift. So with complex structure, of course, high cost. Okay, this we can write for almost all disadvantages we can write. Okay, high cost, complex structure, everything. So that people are familiar with how to do. Then the possible arrangements: linear array. In linear array, elements fed with a common phase shifter arranged in a vertical manner with respect to each other. So it is nothing but a line linear arrangement and a common phase shifter. Phase shifter will be common. That means the relative phase shift between each and every element will be common. Okay, the next two adjacent elements will be having equal phase shift. Okay. In arranged in a vertical manner with respect to each other. Simple arrangement. Disadvantage: since it is a linear array, disadvantage is what? In linear plane only, deflection is possible. Okay, that's it. It's just you can go through. There's nothing much. Planar array. Each element with its own phase shifter. Okay, so you can control the phase shift of each and every element separately. That means the two immediate elements may not be having equal phase shifters, that we can change based on our requirements. Elements arranged in a matrix form. So since it is planar, elements are arranged in a matrix form. Okay, the matrix form the elements will be arranged. So it is in a plane. Okay, in a 2-dimensional plane. So like a chessboard, we can arrange the elements. Advantage: yeah, here the advantage is, of course, beam steering is possible in 2 planes since it is planar. Okay. The disadvantage: complicated arrangement, of course, and more electronically controlled phase shifter needed. In the previous case, we were needed only one phase shifter, that is common to all. Okay, but here, each and every element is having separate phase shifters. So, of course, the arrangement is complicated. Next one is the frequency scanning array. Here, the main beam steering occurs by the frequency scanning of the exciter. Okay, the beam steering is a function of the transmitted frequency. Here, the main beam steering occurs by the frequency scanning of the exciter. Exciter means that the element which we are using to excite the antenna elements, or basically the elements from which the current is coming to the antenna elements. So here the beam steering is a function of the transmitted frequency. Based on the transmitted frequency, the beam steering will change, or the direction of main lobe will change if we are using a different frequency. For a particular frequency, the direction will be fixed. Okay. The normal arrangement is to feed the different radiating elements from one folded waveguide. Okay. So the different radiating elements, that means the different antennas are fed from one folded waveguide. From one waveguide, they are feeding all the different antennas. By changing the frequency, the angle between the axis of the main beam and normal of the array antenna changes. That's how here the beam steering is occurring. By changing the frequency, angle between the axis of the main beam and normal of the array antenna changes. Okay, the angle is going to change since it is radiated from a folded waveguide. Okay, if the transmitted frequency rises, then the beam travels up the face of the antenna. If the transmitter frequency falls, then the beam travels down the face of the antenna. Okay, it's just like this. Since it is directly fed from a waveguide, you might have studied in your this EMT. So, if the transmitted frequency rises, the beam travels up the face of the antenna due to the angle between axis or main beam of the antenna is changing. Okay, and if the frequency falls, then the beam travels down the face of the antenna. As the frequency is varied, the beam axis will change and scanning can be accomplished in elevation. Okay. Frequency, if the frequency is, we are increasing the frequency, the beam travels up, or if we are reducing the frequency, the beam is traveling down. Okay. And for a particular frequency, we can have the planar direction also. Okay. So that's it. That's all about beam steering. It is just a theory. You can just go through that. There is nothing much to say. So now we are moving to the classification of antennas. There is a basic general classification of antennas, and then we will move on to the subcategories. Okay, it's a general basic classification. Then we will move on to the subcategories. So antennas are classified into two categories generally: resonant antenna and non-resonant antenna. Okay, here you can see two radiation patterns. Okay, one on the left side and one on the right side. Okay, can you say which belongs to resonant antenna and which belongs to non-resonant antenna? Which radiation pattern belongs to the resonant and which radiation pattern belongs to the non-resonant? You people are already studied. There is one on the left and one on the right. Which belongs to resonant and which belongs to non-resonant antenna? First one, resonant. First one, resonant. Yes, 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 yes. Why? The answer is correct only. This one. This one is resonant antenna, and this is non-resonant antenna. Or how you have come to that conclusion? Okay, if you are having the notes I have given, in that it is given. Like I am just arranging this presentation based on the notes only, because in the notes I have covered everything. So in the same manner only, I am following the presentation also. Okay, what's the reason? Why I said that the first one is resonant and the second one is non-resonant? What's the reason for that? Symmetry. Yes, symmetry. Just symmetry is okay somewhat. Just polish that. Yes, bidirectional. Bidirectional. Yeah, bidirectional. Correct. That's the correct word. Bidirectional. You can see the two radiation pattern. One is bidirectional, and the other one is unidirectional. You see here, this is a bidirectional pattern. That means it is having the major lobes towards both the directions, towards this direction and towards this direction. It is having the major lobes. Okay, and here it is having major lobes in only one direction. So this corresponds to resonant antenna and this corresponds to non-resonant antenna. Or you can basically say that the resonant antennas are having bidirectional radiation patterns, while non-resonant antennas are having unidirectional radiation patterns. Okay. So we can see first the resonant antenna. So these just points to remember. There is nothing much to teach in this. Length of antenna will be exact multiple of lambda by 4. That is basic thing of resonant antenna. So the length of the antenna can be lambda by 4, lambda by 2, 3 lambda by 4, lambda, like that. It will continue. Okay. It will be exact multiple of lambda by 4. And the main thing is antennas are open at both ends. Okay. Antennas are open at both ends. They are not terminated in any resistance. Antennas are open means this is understood. They are not terminated in any resistance. Used at fixed frequency. Okay, for particular frequency, particular antenna will be used. So that we can understand, since the antenna will be exact length of the antenna, lambda before means it is having a relation between the frequency. Okay. In these antennas, incident and reflected waves exist. That is, standing waves exist. How that can be possible? Okay, here we have already seen that these antennas are not terminated at any resistance. Okay, at the edge of the antenna, we are not at all using any resistance. So that will be open circuited basically. Okay, that will be open circuited. So open circuited means the resistance will be, there will be infinite resistance. Okay, so a wave which is coming through the antenna, first what will happen? It will feel like after the antenna or at the antenna edge, it is terminated abruptly. So it will feel like there is infinite resistance. Infinite resistance means what? The wave will go and it will reflect and come back, because the wave is feeling infinite resistance in the forward direction. Okay. So the wave will reflect and come back, and we can say that a standing wave is present inside the antenna. Okay. Standing wave you might have studied. You have studied in your EMT. Okay, transmission lines. In the transmission lines, in that portion, you have studied how the standing wave is occurring, voltage standing wave ratio, VSWR, all those things you have studied. That same idea only. Here also we are using VSWR is due to the reflection of wave at the end. Here also same. The wave will get reflected and a standing wave will be present in the antenna. So it is called standing wave antennas. Patterns are bidirectional. Okay. Patterns are bidirectional, radiation pattern or bidirectional that we have seen. It is also called as periodic antennas. Just remember these points. Second, non-resonant antennas. Here, the length of the antennas is other than the multiples of lambda by 2. That means it should not be any multiple of lambda by 2. That is the only condition. Okay. At one end of the antenna, it is excited and the other end is terminated in characteristic impedance. Okay. That is the major difference here. In resonant antennas, those antennas were kept open. They were not at all terminated at any resistance. But in non-resonant antennas, the end of the antennas are terminated at characteristic impedance. Okay. What is the specialty of characteristic impedance? Characteristic impedance is the impedance of the free space. Okay. Characteristic impedance is the impedance of free space. So these antennas are terminated at characteristic impedance. So this operates over a wide range of frequencies. So you can say that these antennas are wideband. Okay. So here there are no restrictions. The length of the antenna should be exact multiple of lambda by 4. Like that, no restrictions are there. So you can use it over a wide range of frequencies. There are no reflected waves on this antenna, hence no standing waves. That is a major difference. Okay. Since I already asked you what is the specialty of characteristic impedance, the characteristic impedance is nothing but impedance of free space. Okay. Or impedance of air, we can say. So an antenna is located and it is terminated in the characteristic impedance. So a wave which is coming through the antenna, it will feel like, since it is terminated at the characteristic impedance, it will feel like characteristic impedance is equal to the impedance of the atmosphere, okay, or air. So the wave is coming through the antenna and it is going through the characteristic impedance. And again, what is it is going to see? It is going to see the same impedance in the atmosphere also. So basically, it will continue its motion. Okay. So it is not at all getting reflected since it is terminated at the characteristic impedance. So since it is not at all getting reflected, there won't be any standing waves. Okay, I'll say once again, I will explain this. The wave is coming through the antenna, and it is at one end of the antenna, it is terminated at the characteristic impedance. So the wave will go through the characteristic impedance, and next it is the atmosphere. Okay, in the atmosphere also, characteristic impedance is only the wave will feel characteristic impedance only in the atmosphere also. So since it has already been traveled through that characteristic impedance, it will feel like it is again traveling through the characteristic impedance, and the wave will travel through the atmosphere. Okay. That is the basic difference. So there won't be any reflected waves. So there won't be any standing waves. So it is called traveling wave antennas. The wave is just simply the wave will travel through the atmosphere from the antenna. So it is called as traveling wave antennas, and it produces unidirectional patterns. Now, can anybody tell how unidirectional pattern is coming for non-resonant antennas and a bidirectional pattern is coming for resonant antenna? Can anybody tell? We have explained this so far. And can anybody tell how this bidirectional is coming for resonant and unidirectional is coming for non-resonant? Okay, any answer? Yeah, nobody is answering. Okay. You see, there is a reflected wave. There is a reflected wave in the resonant antenna. Okay. And in non-resonant, the wave is just traveling. That means the wave will go in that direction only. So we can say that the radiation pattern will be unidirectional. But in non-resonant, there is an ongoing wave and a reflected wave. So we can say that the radiation pattern will be in the two directions. So resonant antenna will be bidirectional and non-resonant antenna will be unidirectional. Okay, that is the justification. So it is also called as a periodic antennas. Why resonant antennas are called as periodic antennas. Okay. Now we will move on to the antenna. Okay. This that based on the structure of the antennas, we are again classifying. The non-resonant and resonant are the general classifications. Okay. So next is the based on the arrangement and structure, we are going to classify the antennas. The antenna. It is an antenna in which the conductors are arranged in the V shape. That is the basic reason for the classification. And the conductors are arranged in V shape. It FedEx apex and included angle. Length and elevation are chosen to obtain desired directional properties. The feed line is shown. There only we are giving the feed. Okay. And the L1, L2 will be the lengths of each legs. Theta 1, theta 2 will be the elevation, angle of elevation of the two legs. By appropriately choosing L1, L2, theta 1 and theta 2, we can obtain desired directional properties. Okay. Excitation to each wire is out of phase. Okay. Each wire will be fed with same signal with opposite phase or out of phase. Okay. It offers greater gain and directivity when the length of each leg or wire is increased. We are increasing the length of each leg or each wire, greater gain and directivity we can achieve. Radiation pattern can be unidirectional or bidirectional. That is the thing here. It can be, radiation pattern can be unidirectional or bidirectional. That mean, what does that mean? this particular V antenna, we can arrange it as resonant form and non-resonant form. If we are arranging it in resonant form, we will get bidirectional pattern. Okay. And if we are arranging it in non-resonant mode, we are going to get unidirectional pattern. So pattern of resonant V antenna is shown here. How the pattern of a resonant V antenna looks like. See, resonant means what? We are not at all going to terminate that in a particular resistance. There won't be any resistance. Just we will arrange it as V. Okay, so there will be a reflected wave. So if we are just arranging like this, as shown in this figure, we will be getting a resonant V antenna with bidirectional radiation pattern. Okay, that is only shown here. Okay. Next one, non-resonant antenna. In non-resonant antenna, what we have to see? The antenna is V antenna only. Just terminate it with characteristic impedance. That's all. Okay, just terminate the antenna with characteristic impedance. All other things are same only. Pattern of non-resonant antenna is as below. To achieve unidirectional pattern, the open ends are terminated in characteristic impedances. That's all. Okay. So if we are terminating the open ends with characteristic impedances, we are going to get a unidirectional radiation pattern. Okay. While in this, we were not at all terminating the ends with any resistance. The ends are kept open. So at that time, we will be getting a reflected wave, a standing wave will be formed, and as a result, we will be getting bidirectional pattern. Both these arrangements are V antenna only. Okay, one is resonant V antenna, and the next one is non-resonant V antenna. Accordingly, we will be getting the radiation patterns as bidirectional and unidirectional. Okay. So next, using V antenna, end fire and broadside antennas can be easily constructed. Now we are going to use this V antenna to construct end fire and broadside antennas. Okay, what is end fire antenna? It should fire towards the ends. Okay, firing direction should be towards the ends. So here you can see in this figure, you can see the direction of maximum radiation or firing direction will be towards this direction. Okay. So one V antenna is arranged like this. It will be radiating to this direction. Another radiation, another V antenna is arranged like this. It will be firing like towards this direction. And likewise, the maximum direction of radiation will be towards this direction or towards the end of the array. Okay. This is the end fire arrangement of V antenna. And here the broadside arrangement of V antenna. Okay, V antenna. This is a V antenna, and this is another V antenna. Okay, likewise, this is one V antenna. This is another V antenna. Likewise, we can arrange. So it will be. This is the array axis. Array axis will be like this. So to which direction it will fire? It will fire towards this direction. Okay. The firing direction will be towards the, or the firing direction will be perpendicular to the axis of the array. Okay. So these are the end fire arrangement, and this is the broadside arrangement of the antenna. Okay. Next, we are just going to see the maximum directivity. Then this is just one equation for that maximum directivity. Maximum directivity is given by 2.94 into L by lambda plus 1.15 or 0.5. If L by lambda is line between 0.5 and 3, you can use this equation. Okay. So this is only the basic. Generally, L by lambda will be less than 0.5 and 3. Okay. What is L? L is the length of the legs, L1 and L2. Normally, we will take L1 and L2 are same. Okay, lambda is the wavelength. Apex angle, that means the angle between the axes. Okay, the apex angle ranges between 36 degree to 72 degree. Length varies between 8 lambda to 2 lambda. Okay. So, can you say like any disadvantage of this particular arrangement or this V antenna? Can you say any disadvantage of the V antenna? Can you say any disadvantage of V antenna? The length should be between 8 lambda to 2 lambda. Okay, the length should be between 8 lambda to 2 lambda. That means with higher wavelengths, it is not at all possible. If the wavelength is very high, it is not at all possible. We cannot have that much length. Okay, we cannot have that much length for the antenna. Okay, antenna legs, we cannot have that much length. So if the length is, the wavelength is higher, we cannot use this V antenna. Okay. And the main disadvantage is high side lobes exist. That you can see from the radiation pattern itself. You see here, see here also. High side lobes are present. Okay. Even though the main lobe is large, the side lobes are also significantly large. Okay, so that is also another disadvantage, that is high side lobes exist. Applications: transmitting and receiving antennas in the high frequency band. The V antenna, they are mainly using in the high frequency band. Okay, transmitting and receiving antennas, they are using as transmitting and receiving antennas in the high frequency band. Okay, so this is the major application of V antenna. Okay. So next topic is rhombic antenna that we will be covering in the next class. Okay. So I think we have almost done a review of up to this V antenna. We are almost done. So next class onwards, we will be having review of the remaining portions. Or if you have any particular suggestions, you can tell me. Or like if you want to take any particular topic, you can tell me. We will doing that rather than revising for the 5th modules. Okay. Or if you want to do any particular problems or something like that, you can also tell me. We will be doing that in the classes. Okay.